Talk is by William Irvine, University of Chicago. I just learned that he was an undergraduate in Imperial and spent time in Italy, so he's been around, and we will see marvelous things about knots in lights and fluids. Start.
Thank you. So I should begin by thanking the organizers for the invitation. It's a pleasure to come back and talk to you. It's been a very stimulating meeting so far. And in preparing this the other day, I realized in a moment of panic I'd sent a very overambitious abstract. I promised I would tell you about two things. One represented here on the right are some experiments with vortex loops. And the other represented here on the left is some analytical work in which we've been looking at solutions to Maxwell's equations, where the field lines are knotted and linked in a non-trivial way, and in particular at finding conditions under which the evolution of the field can be described by a smooth diffeomorphism, or analogous to a fluid flow, preserving the knottedness in the field. And it's all analytical, and there's lots of things I'd love to tell you about, but there's no time to do all that, and I'm happy to talk. I'm just saying this because I'm happy to talk to people afterwards who are interested. But what I thought I would do, given the context of the last few days, is tell you instead only about our experiments. And these are experiments in which the goal was to create vortex loops, like smoke rings, but tied into knots. And it's sort of hard to talk about this, especially over here, without paying homage first to where it all started, Lord Kelvin. We've heard a version of this in the last couple of days. There's a story that goes with this, which he was attending a lecture, and part of this lecture was a demonstration by Tate, and the demonstration must have looked something like this. He was producing smoke rings which traveled across the room. This, of course, is not Tate. It's Dustin Kleckner, the postdoc in my lab, who's been working on these experiments together with a student, Martin Schieler. Anyway, so this was still the time when the ether was in fashion, and nobody really knew what atoms were. And the story goes that seeing the stability and the simplicity of this elementary kind of topological excitation of a fluid, Kelvin conjectured that in fact atoms were such knots tied in the ether. Okay? And you could reproduce the entire complexity of the periodic table by having different knots, and you can imagine having reactions as reconnections and knotting. And even, I think he went a little further to try and predict spectra through vibrational knots. Anyway, so this is an example of a beautiful idea, which of course failed in its intent to describe atoms, but nonetheless was very profound and started something. And one of the mechanisms by which it started something was the table which Tate was inspired to create, presumably to find a mapping onto the periodic table, which then was sort of a gauntlet which had to be dealt with, and out of that, to some extent, was born knot mathematics, which has, of course, later come back into physics in many, many different contexts. One example is sort of exotic field theories. Another one is magnetohydrodynamics and plasma physics. And I just want to point out with this slide some sort of recent developments. I think now is an exciting time to study these problems, partly because of developments in both experimental control, but also our ability to visualize and use some of the mathematics which was developed. And so an example over here is some recent work only in the last few years, some work on light, which I won't tell you about. There's some work on knotted vortices in optical beams, which you heard about from Mark Dennis the other day. And some beautiful, this was experimental as well as theoretical, and some beautiful experiments in the group of Ivan Smaljuk, and also in Ljubljana, in which they studied knotted and linked liquid crystal lines. And all these systems might seem like very different problems, but in a practical sense, they have in common a set of problems, which is sort of how you design the initial state, how do you think about the rules that in a topological context for the evolution and stability of the structure, and how do you couple between them. So there's a sort of topological design problem. And so this is part of the motivation for what I'm going to tell you about. And the other, of course, comes from what we've all been hearing a lot about in the last few days, which is problems to do with vortices themselves in superfluids and classical fluids as a means to understand phenomena such as turbulence. And of course, in this context, a particular aspect of this problem is there is a conserved quantity in the inviscid case, and somewhat dissipated, but everything is dissipated in the viscid case, which is helicity. And as Keith showed us many years ago, this has a topological interpretation. It's a quantity which measures the knottedness, the degree of tangle and knottedness of vortex tubes or vortex lines in a flow. And we wanted to sort of try and study this. And I think it's fair to say that there's been a lot of work on this subject over many, many years, a humbling amount of work. But in experiment, at least, in the vast majority of cases, this is focused on very complex tangles and very complicated situations. And what I sort of wanted to try and do was to create a system in which we could study this problem in a clean fashion, just creating isolated knots and see if we could probe the extent of these conservation laws through their dynamics. And also, of course, it's interesting for many other reasons, just vortex dynamical ones outside of the knotted context. So as Dustin, who's also a master at Photoshop, likes to put it, we're going to take these beautiful rings that the dolphins make, and we're going to try to tie them into knots. Okay, so a noble goal, at least I thought. How do you do it? And you can think of sort of various ways. It turns out I discovered this afterwards. The first way that we tried it, in fact, being tried by many people, and it's a sort of natural way. You try to take different rings and you try to collide them together and see if you can form a knot. And here's an example, for example, of a proposal of how to do this by Renzo not so long ago. And he suggested that if you take a pair of vortices, and they're not like nice smoke rings, not nice and circular, but you've perturbed them so they're wobbly a little bit, and you shoot them at each other in just the right way, then you might be able to get them to reconnect in a special way and end up with a knot. And whether or not this is the proposal, any such proposal is going to have a few ingredients, and these ingredients essentially are that you need to have a fine trace of the core of a vortex so you can see it and make it. You want to be able to control it. You want to be able to control its shape, and you want to be able to control the sort of timing with which you shoot things. So to introduce our system, what I'm showing you over here is the simplest experiment we've done in this context. It's just a single smoke ring production. So this is, in fact, a vortex ring in water. This is a water tank. There's a hole in this tank, divides the tank into two. And on one side of this tank, there's some bubbles in the water. And on the other side, there are antennae. And you're looking at the hole head on. And if you push the fluid through the hole, the bubbles immediately get attracted to the core of the vortex and give you a fine trace of it. And this is just buoyancy. You have vorticity around the core, and so anything which is lighter than water will be attracted to the core. And it gives you a nice trace of the core compared to smoke. So the next thing which we did was start to play with shapes. And this one is an experiment in which we took a hole, which was not circular, and pushed a shaped vortex out of it. And you can see it has a very coherent motion. If you get things right, you let the flows die down, and you're careful, you can engineer these very coherent motions in vortices. And you can see that it persists over quite a long time. In a moment, it's going to dissipate, but that's just because there's a wall here, a transparent wall you don't see. And it's a nice example for many reasons, not only to show the experiment, but also because it can be used to illustrate how the evolution proceeds. And the first order, the evolution proceeds as predicted by the local induction approximation. The velocity of a vortex is proportional to its curvature, so the more curved parts over here are going to go faster, and the anti-curved parts, if you want, here are going to go backwards. So in fact, what this object is doing when you look at it from the side is it's having the fast parts coming in and the anti-curved parts coming out. It's sort of flapping. And you can understand this, as I said, in terms of local induction. So this is one ingredient. And the other one is timed sequences. And this is a reproduction of a famous experiment with vortex loops. I'm shooting two rings. And you can see from the side how they interact in each other's flow field. And it's possible to get reasonable control over this too. And there's a lot of movies like this that I could show you. But we don't have that much time. And in fact, in the end, this whole approach fails. And the reason it fails, you can sort of infer a little bit from what happens next. You see, when these two loops interact and recombine, it's a very delicate process. And in fact, when you get these reconnections, you typically get disturbances that interfere with this process and make it very hard. So we were a little depressed at this point. But we thought we'd try a different approach. And the next thing that we tried was to make a hole where the edge of the hole is a knot. So what you see over here is just a plate. We bolt this onto our tank, onto a big hole this size. And then the idea is that we push fluid through this hole. And the edge of this hole is a knot. And again, I would love to show you lots of tries. This was try number 8. But let me cut to the point. And the point is that this also failed, but this failed in an interesting way. It failed, in fact, it worked everywhere where there was a broken symmetry. It worked everywhere where you had a hole on one side and solid on the other side. But everywhere that you had a hole on both sides, it failed. And the reason it failed is essentially what you have over here, if you think about it, is 4 holes pointed at each other, and you're going to suffer from all the same problems. But if you want to make a knot, you're always going to have this problem. So what you need is an object that breaks symmetry. And the object that breaks symmetry is, in fact, what brought us all here to this meeting. It's a wing. You can think of the flow around a wing, which is sort of carrying you, as a sort of superposition of a circulatory motion around the wing and a steady background flow. And this achieves the lower pressure above than the higher pressure, the lower pressure above than it is below. And this works very well as long as you're flying along, but when you're on the runway, of course, you're not buoyant, you're sitting there, you have no circulation. So in the process of accelerating, you must be generating this circulation. But circulation, we know, is not something you can sort of willy-nilly generate. There's some sort of rules for that. And the result of that is that, in fact, when you accelerate and produce circulation around the hydrofoil, you need to emit a vortex which balances that circulation. This has nothing to do with the edge vortices, of course. Those are finite size effects, which an infinite wing or a closed wing would not have. These are an acceleration effect. And so you can imagine taking a wing and tying it into a loop and accelerating it. And this could be a way of generating a vortex that breaks symmetry. So this is our wing. And if you accelerate it, indeed you can make a vortex loop. And this method actually works quite well for loops. You can go and look at them quantitatively. They have produce a ring with a nice steady radius. They scale the right way with the circulation, the acceleration. But the interesting thing about this isn't so much the starting vortex, that's a sort of known phenomena, but the fact that once you use that, now you can think of doing something like this. And of course, if you want to make something like this, you need to choose a shape for your knot. And we chose the shape which comes from the analytical solutions by Shirige Okida in the local induction that predict a shape that moves without change of form whilst rotating and propagating. So this time I'm not going to show you a failure. And in fact, I was talking the other day with someone, and the first question they asked was, "You're going to show me the best data you ever got." And I'd just like to point out this is in fact the worst data we ever got, but it's the first data we ever got, and we were very excited when it worked, so I wanted to show you this. So we're going to accelerate this into the board. And if you design the right shape of hydrofoil, you can get it to knot. I'll just show it again, a little bit faster.
Is this all seated with the air bubbles?
Yes, air bubbles were attached to the hydrofoil. We can also do this with air bubbles everywhere. There's no difference. It's just a little clearer this way. Okay. Now, some of you might be thinking that's not an orange knot at all. It's a blue knot. And we all know from last night the tricks that you can play with a blue knot. And so what I'm going to do next is I'm going to try to convince you that this is not, in fact, a trick. The two-dimensional image that I'm showing you is, in fact, corresponding to a knot. I'm not masking anything. And to do this, we created a setup in which we could take a laser sheet and just scan it back and forth. We do this at a high rate. But if we synchronize that scanning with a camera, we can then capture the three-dimensional shape of the vortex. And then we can look at it in 3 dimensions. And so this, I hope, is convincing evidence that, in fact, we have a vortex knot. This is raw data, by the way. Okay, so we have a knot. Okay. Now, the first thing which is sort of instinct is to do is to sort of poke around and play with it a little bit. Is this, is this method really working? Did we just get lucky with one time? What's going on? And you'll see, in fact, that there's a few wiggles and various features on this vortex that you sort of want to know where they come from.
Is it rotating?
Yes, but we'll come to that. The first thing I want to convince you is that this sort of works, actually. And so we did a series of experiments in which we scaled everything. We made different hydrofoils. We accelerated them to different speeds. And there are sort of two numbers in this. There's a circulation, and there's a characteristic size of the object. And with using these, you can rescale and find a rescale time. And so we took a lot of movies like this. This is now better, more modern data, if you want. And we took them at the same rescale time. And you can see that, in fact, the shape is very reproducible down to the wiggles that you see everywhere. And we were trying to think of a way of quantifying this, and the only way we could think of is, well, instead of trying to make a graph, let's take this data and rescale it in 3 dimensions and overlap it. And if you rescale by the length scale and the time scale, you see it's a very reproducible. So the next thing which we wanted to do was sort of see whether or not we could do other shapes. This is a general technique. And this is a pair of linked rings. And we're in the process of playing with all sorts of other things, Borromean links and the like. Okay. And you asked immediately what happens when it propagates. So how am I doing for time? Mr. Chairman?
3 minutes.
3 minutes, okay. So I'm just going to skip this, and if anybody has a question about this, we can come back to this at the end. Okay, it does indeed rotate. It doesn't, in fact, survive forever. It unlinks through an interesting mechanism, which I'll just show you a very quick preview over here. But what I'm going to do in the next couple of minutes is just spend a little time talking about the future rather than this generation. And one thing which I want to tell you about is the fact that we can now reconstruct in software from the raw data the shape of the core. We can then use this to infer the flow field and look at quantities like, well, the strain tensor of the water, of course, but also things like the energy. So, for example, one of the things which we're doing at the moment is measuring the energetics of these vortices and their evolution and trying to understand this reconnection process through that. But since there are a couple of things which were mentioned a lot in the last few days, I just want to show you, and this is sort of the future of also the measurements which we're doing. There are 2 phenomena I want to show you that we can sort of engineer with this control that were mentioned a lot. And these are reconnections and Kelvin waves. And so this is just to show you our way of imaging. This was an early video, actually. Corresponds to that knot you saw earlier. But it gives you an idea of the level of control that you have in imaging these processes. In fact, you can already see from this there's a few Kelvin waves being emitted. But you can also engineer coherent Kelvin waves. So this is now a vortex with a Kelvin wave on it. And this is a sort of single frequency version of a Kelvin wave. You can watch its evolution. And in fact, it qualitatively behaves as you would expect. But we're trying to do some quantitative measurements on this. And finally, since these were drawn on many, many cartoons, I wanted to show you our version of a chirped Kelvin wave. This was generated by an engineered reconnection. And you can see the spiraling of the wave and the sort of almost self-similarity of it. So, to conclude, I hope I've convinced you we've found a method to generate vortex knots, and not only vortex knots, but vortex loops of arbitrary shape in 3 dimensions. It's a way to pattern vorticity, and we hope to be using this in the coming years to study many of the phenomena that we've heard about. And I should conclude, this is or an old conclusion, by thanking, of course, the people in my group, Dustin Kleckner, who's a postdoc and actually will be here next week, Martin Sheila, who's a student working on these experiments, and, well, this is Hridesh, who's working on a knotted light, which I didn't tell you about, but there it is. Thank you.
Questions? Yoshi?
Yes.
William, do you predict that Kelvin wave is always associated with reconnection, or well, vice versa? Well,
Do I predict? In this case, I think I'm looking to see whether it's true. I wouldn't make any predictions.
Other questions?
What kind of equations you consider? Because all notes and so all nice pictures we can obtain, it's no question. But what is the system of equations which you study for example, in your...
Well, I mean, one question, for example, is I mean, there are many open questions as to topological excitations, isolated ones. Can you have one that survives forever, for example? Or is this reconnection mechanism a universal one? And when you consider questions like helicity, and if you want to study whether or not helicity is conserved through these topology-changing reconnections, then the only experiment in which, to my knowledge, you can do this is one in which you start with a non-trivial topology. So we're going to be looking at helicity conservation. But beyond that, I think there's a sense in which the dynamics in this system, at least at the vortex level, are not necessarily so different from a lot of other systems. And so we want to study reconnections and the dynamics in these filaments to see if maybe we can understand something about vortices in general cases. Sort of slow build-up to more complicated flows.
I think that's all we have time for questions, so you can talk more over the break, coffee break.